Matter we said that matter emits photons when it's got charges that are accelerating. It absorbs photons when charges respond to the photons by absorbing the energy in the force that the photon exerts on the charge. We'll look at rotation. There's three different ways that we're going to talk about. And these are I think these are everything, unless we start looking at magnetism and stuff like that. But when we have a molecule that is polar, and polar is something that we're going to get into later, we'll explain this later, but a polar molecule essentially means that we've got a charge separation across the molecule. There's one side of the molecule that has more electron density than the other, and so it's negatively charged on one side. And the other side is depleted of electron density, and so it's positively charged. So just for a generic polar molecule, I'm going to draw a circle. We'll stick a positive charge here and a negative charge here. What this means is that this is some generic distribution of nuclei, but the net result has been that the majority of the electrons have been sucked over to this side of the molecule, leaving a depletion of electrons over here, right? In the case that you have a polar molecule that is rotating, this molecule can absorb photons by exciting its rotation, by causing it to rotate faster. And to understand this, we're going to have to take a look at this. Keep in mind, this is the weird part. A photon itself occupies a volume. It's not necessarily a particle. It's both a particle and a wave. And the wave nature of the photon creates a situation where the photon occupies a volume. The volume occupied by this photon is comparable to the volumes found in electron distributions, matter distributions of electrons and protons and whatever. And so I'm going to ask you to imagine for a second that I have a photon that occupies some volume, and that by occupying that volume that's comparable to the size of the molecule, this photon can act on all regions of this molecule at the same time. Okay? That means that the fields that are present in this photon, remember we've got oscillating fields in that photon, are exerting forces on not only the positive charge, but the negative charge simultaneously. Now let's imagine that this molecule is rotating. We got this end of the molecule. I'll do it this way. We got this end of the molecule moving down, and this end of the molecule moving up. Now, what that means is that if we draw the photon as a point in space that's acting over the molecule, as the photon hits the molecule, say the photon is in this position, it's generating forces upward, or in this case upward and downward, on one charge, while simultaneously it's acting to cause forces in the opposite direction on the other charge. So a photon will have opposite effects on a positive charge and a negative charge, equal and opposite effects. It'll push the positive charge in one direction and the negative charge in the opposite direction. If that photon strikes this molecule with just the right orientation, it will pull the negative charge downward while simultaneously pulling the positive charge upward. It creates a torque on that molecule. And again, if the orientation is exactly correct, it will pull this end up at the same time it's pulling that end down, and then the sine wave will flip directions, and it'll cause another torque on the thing where it's pulling one in one direction and the other one in the opposite direction as the photon passes over the molecule. So imagine you had a spinning ball, you got a ball, you're spinning on your finger, and you apply the forces in the direction of the turn. The photon does that on both sides of the rotating molecule and speeds it up. And now the energy from that photon has been absorbed by the molecule. That's rotation. Something about the push. I was trying to figure out how to explain this, and it occurred to me I had a perfect way to explain it. I was pushing a kid on a swing the other day at a park. And if you time the push of your swing with the travel of the kid, you'll cause them to swing larger distances, right? While they're going that way, you push that way. When they're coming this way, you pull that way. You gotta time your push with the oscillating motion already in the body, and if you do so correctly, that body absorbs your energy. If you do it incorrectly and you don't time the push, the person on the swing will slow down, right? If you're pushing that direction while they're coming this way, then you take away their energy. Well, that's kind of what we're talking about here. This photon has to line itself up perfectly so that it's pushing that end down, pushing that end up, and so that when the photon switches direction, it's still causing equal and opposite torques, increasing the spin. Now, we'll talk about vibration. When you have a molecule that is polar and is vibrating, you can also absorb a photon. So for a vibrating molecule, I'm going to draw this guy right here. And this vibrating molecule has to have, it doesn't have to be a polar molecule, but the vibrations have to result in a change in polarity. It's a little weird. Again, it's not for this class. You'll learn this stuff in other classes, unless you don't take those classes. Just imagine for a second that we have a molecule that when it's at one end of the vibration, the charge separation is large. But then when the vibration changes and it goes to the bottom of its vibration, the charge separation is smaller. Well, as the molecule vibrates then, you got positive charge and negative charge that are moving with some periodicity. The photon can interact with that moving charge distribution in a way that is highly similar to the way that it interacted with the rotating charge distribution. If the photon hits this thing, again, the photon's acting over the whole molecule. If the photon hits this thing with the right orientation, it'll cause, if say the molecule's in the inward push of its vibration, it'll push the positive charge down, and it has opposite effects on the negative charge, and so it'll push the negative charge up. And so the photon will aid in the compression of that thing. Now, if the photon is hit with the right orientation, such that it changes its direction, the photon changes its direction at the bottom of the push, as soon as that thing changes direction, it'll exert oppositely directed forces on this guy. And so now it'll push the positive charge up and the negative charge down. Just like when you're pushing that kid on the swing. You gotta time your push, but if you time your push just perfectly, you'll transfer your energy into the kinetic energy of the object. So the photon that hits with the right orientation, we slam that spring down, and then right at the bottom of the compression, the photon flips its direction, the direction of the fields change, it pulls it back out, and those forces from the electric fields have acted to take the energy from the electric fields and to use it to increase the kinetic energy of the molecule. Okay? So that happens. That's what you got to understand vibrational spectroscopy. Okay. Now,
are you going to use the equations in this course?
not really. The R-squared force law equation, I don't have any exam questions that ask you to use that. At least I didn't last semester. There's a chance I will this semester. But in general, no. This is a Gen Chem class. We're asking Gen Chem level questions. And the questions that you get asked on your homework will be of the order that you have to concern yourself with.
I don't understand what's the H stand for.
Huh?
In the equation, what's the H stand for?
Oh, that equation. I thought you were talking about the R-squared force. H, Planck's constant. So Planck's constant is a constant that relates the energy, and this was empirically derived. They did experiments that showed them what Planck's constant was. But essentially, it's the equation that relates the energy to the frequency of the photon, right? Okay, so I just told you that for rotational and vibrational spectroscopy, the fields of the photon interact with the charge distribution to cause forces on it. And those forces can cause energy to be absorbed by the thing. Yada, yada, yada. The energy that's absorbed will be the energy of the photon. Now, there's another way, so this was rotation. There's another way the charge distributions absorb photon energy. This is vibration. And that last way is electronic. It's not as easy to explain electronic transitions, electronic excitations as it is rotational and vibrational. It has something to do with the transition dipole. And I do not want to open up that can of worms right now. But you've already seen that photons can exert forces on charges because photons are simply electric fields, right? Or propagating electric fields. And so it shouldn't be a surprise to you if I were to tell you that a photon can act on a molecule to move charges around. You should know that the charges in a molecule that move are mostly the electrons. The protons have so much mass that when they're acted on by a force, they don't move around much. And so mostly, when a photon hits a molecule, what it does is it moves electrons to higher energy positions. And if a photon strikes a molecule in just the right way, it'll take an electron from a low energy position and it'll move it into a high energy position. That high energy position is usually an orbital, an electron orbital that has usually a further separation distance from the nucleus. And so you can kind of use this thing that I'm going to be showing you over and over again to understand electronic transitions. When you've got positive charge and negative charge stacked right on top of each other, they're a low energy position. You've got low E, right? Now, we stick a photon in, and what that's going to do is it'll tend to move the electron and proton to further separation distances. You always have to consider kinetic energy, and there's some cases where it's not absolutely true that the electric potentials are what changes in the photon absorption, but it's usually the electric potentials. And so we take a photon and we allow it to coherently strike this charge distribution. And it'll take that electron and it'll bump it up to some higher energy level. Yeah? Now, to start playing with that concept, we're going to introduce the Bohr model, talk a little bit about the Bohr model, and we'll draw the results of the Bohr model. Where is my mind? So we already talked about this a little bit. Hey, what time does this class end? 3:10. Does it? So you'll be able to dig these notes up and read them on your own. Essentially, they just reiterate in greater detail the conversation we just had. So Bohr is sitting there and he's trying to figure out hydrogen. Hydrogen's got particular emission spectra, blah, 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 blah. It's all about energy. Bohr knows this. And so he tries to build an equation that will predict the energies available to a hydrogen atom and use those to explain its emission spectrum. Bohr needs a couple of things to build this. Now, first of all, his job was really easy because in the hydrogen atom, this equation holds largely. When you've only got one proton and one electron interacting, the forces look a lot like this, effectively exactly like this. And energy is the integral of force over distance. And so if you want to figure out the energy of an electron that's sitting next to a proton, you integrate that force over whatever distance traveled, right, and get the energy. And so Bohr needed that to calculate the electric potential energy. That's the electric potential energy we're talking about. The kinetic energy comes somewhere else. He uses this equation for the electric potential energy, the integral of this equation. And then he takes a standard figure for the kinetic energy, Ke is equal to 1/2 mv squared. And he puts these things, these two pieces together, along with the information that, that there's a balancing of forces requisite to hold an electron in orbit around the proton. So we talked about this the other day, loosely, but when you've got an object that's rotating about some point, right here, we got a guy sitting here in the center, and he's got a string, and that string has an object on it, and we're rotating this in circles. Well, right here at this point, this thing that's rotating has a tangential velocity that's pointed in this direction. A couple seconds later, this thing is at a new point in space, and its tangential velocity has changed. It's now moving in this direction. Well, you don't change your velocity unless you're acting on the force, right? To accelerate, which just means your velocity changes, you have to be acted on by forces. So for uniform circular motion, they noted that in order for this thing to keep rotating, it's got to be subjected to an inward force. There's got to be some force causing an inward pull on this rotating object to keep it from simply traveling out that way. So there's some force acting on any rotating body to accelerate it inward, right? Or basically just noted that that force that would cause the electron to stay in orbit must be caused by the attraction between the positive charge and the negative charge, right? So you've got a balance between this electron wanting to fly out of its orbit and the attractive forces from the nucleus that keep it bound. He noted that guy. And so that's what this term is right here. E squared over 4 pi E naught R squared is equal to mv E squared over R. Balance between the forces on the nucleus, or provision of by the forces between the nucleus and the electron for that acceleration required to keep circular motion. Bohr did one other thing, and he noted, and we just talked about how photoelectric effect let them know that the photon was also a particle. Well, they had similar diffraction studies that allowed them to figure out that an electron was actually a wave. They just recently figured out that things that we don't think of as waves, matter, is actually a wave. The concept of a matter wave was born. And so Bohr noted that he wasn't allowed to think of that electron just as a point in space. He had to think of it as a wave. And from matter waves, they had derived this equation right here. This one that says that lambda is h over p, where p is the momentum of the particle. So a matter wave follows this equation right here. Its wavelength is going to be equal to Max Planck's constant divided by the momentum of the particle. We're not going to ask you to use this equation here, but if you're a physicist, you're going to have to eventually. But you need to note that is a description of the wave nature of matter. And so Bohr did one more thing. He had envisioned these orbits. And the way that he envisioned them wasn't exact, but it did the trick for hydrogen. Let's look at this for a second. Bohr envisioned these orbitals where electron moved in a spherical fashion around the nucleus. And he said that in order for the electron to not eventually cancel itself out, that it had to have an integral number of wavelengths that it went through as it moved around the nucleus along its path. If this is not the case, what happens is you take a path around the nucleus, and by the time you get here, or by the time you get back to where you came from, your field isn't in the same direction or orientation that it was in before, and so it actually cancels itself out. And that doesn't fit the description of the real world. Electrons don't just spontaneously disappear, right? So he said that in order for that electron to stay around, that it would have to be in phase, it would have to stay in phase during its entire orbit, or the phases would have to be the same at every single time it reached a given point in space. What you can do with that, what Bohr did, is he envisioned these circular paths where the path involved an integral number of wavelengths around the orbit. And so the condition was held that the first orbit would have, and I don't even know how to draw this, it would have a wave nature where, I'm a horrible artist, where it went through exactly one wave cycle over its orbit. And the next orbit, he said, it would go through like 2 wave cycles. And the next orbit, and in order for that to happen, for the integral number of wavelengths, each of these orbitals would have to spread out further distances away from the nucleus, right? And so the third orbit would have like 3 cycles. That's not 3, that's 3. 3 cycles that it went through in its path. And so Bohr started essentially envisioning different orbitals that surrounded that hydrogen nucleus, where each orbital had one more wavelength of travel. So in this orbital, you go 1 lambda when you move around the circle. In this orbital, you get 2 lambda when you move around the circle. In this one, you get 3 lambda. Here's what he did next. He took all of those equations and he put them together and he came up with an equation. So we know the wave nature of the electron. Its wavelength is Planck's constant divided by its momentum. We know here that the distance, 2 pi r, around the orbital has to be equal to an integer number of wavelengths in lambda. Took that expression. Set those aside for a second. And then he put together an expression for the total energy of the atom. Total energy of the atom is going to be what? Kinetic energy plus potential energy. Kinetic energy is 1/2 m times the velocity of the electron squared, standard expression for kinetic energy. Your potential energy, you'll notice, negative E squared over 4 pi E naught r, that's the integral of this force equation. So he was implying that there was a spherical potential that acted on that electron. You take the integral of this potential, you get the potential energy of the electron. Take those 2 terms, we stick them together, and then you make the appropriate substitutions using the 2 equations above, and you will get to this equation right here that says that the total energy of the electron is the mass of the electron times the electric charge to the 4th power divided by 8 pi E naught h squared n squared joules. Basically, that's just that energy expression with the appropriate variables swapped from the top 2 equations. Now here's the deal. I'm not going to go take that myself and reconstruct it into that expression, but if you do it and you put it on a piece of paper for me and you submit it, it's 10 points extra credit. It might be too much extra credit, but I'm going to do it anyway. So if you could take those expressions that we just looked at and you could turn them into this expression here, it shouldn't be that much, it's just algebra, just a few steps algebra. I'll give you 10 points for it. Now, I want to talk for a second about the negative sign on that thing. The negative sign on that potential is determined by your reference point. So the reason that energy is negative is this. Remember what we said, if we got positive charge and negative charge close together, we got to put energy into them to separate them? Well, on the same level, when you allow them to come together under the forces of attraction, energy is released. So what they did is they took, on the potential energy, they took infinity as a reference. So you get a positive charge and a negative charge, and let's say that there is an infinite separation distance. At that point, we're going to call the electric potential energy 0. We're going to say there's no energy in that charge distribution, or released by that charge distribution. But as the electron is allowed to approach the proton from infinity, is energy absorbed or released? Released. If they're coming together and the forces of their attraction, then that electric potential energy is drained from the system. And so that's largely why we end up having this negative term, is because we've accepted as zero potential the situation where the electron and the proton are separated by infinite distance. Something to note. Based on that equation and what we just drew there, the closer that electron is to the nucleus, and that'll be a function of your n value, right? If n is equal to 1 and you're in that first orbital, then you're the closest you can get to the nucleus. The closer that electron is to the nucleus, the lower energy is, just based on what we see in that equation. That's largely a effect of those electrical potentials. As we move from infinity closer and closer and closer towards the atom, that electric potential energy is diminishing. And so your orbitals with lower n values, the ones that are closer to the nucleus, have lower energy. Okay, so you put this all together, you take all those constants in that top equation, and you plug in their actual values, you'll get this expression. The total energy for electron is negative 2.179 times 10 to the negative 18 times 1 over n squared joules. Now, for transitions, we've got electrons in the hydrogen atom. Transitions, we've got electrons moving from one orbital to the other. So you might have an electron that's going from a low energy orbital to a high energy orbital. In that case, energy would have to be absorbed by the system. And if the electron starts off at a high energy orbital and moves to a low energy orbital, then energy would be diminished by the system. You can take delta E as the energy of the final state minus the energy of the initial state. Plug in that equation, and you'll get delta E is equal to negative 2.179. It's either negative or positive, times 10 to the negative 18 times 1 over n final squared minus 1 over n initial squared. And that equation will allow you to predict the emission lines in the hydrogen atom.